just to make sure that everything is in order. If you can see my screen and hear my voice, please type yes in the chat box. You know, thank you. You know, it is kind of lame now. It's kind of boring now that see every time we start the session and I ask you if you can hear my voice, please type yes. It's kind of mundane, right? Probably you type when I ask you that question next time, you type hell yes. How about that? Doctor, start with a joke then. No, I don't have a joke. Okay. I'll tell you a joke. See, there was a guy driving around with some penguin in the back seat, and he was stopped by a policeman, and the policeman said, "You're not supposed to drive. You're not supposed to be driving around with penguin at the back seat. So please bring the penguin to the zoo." And then the policeman let the man go. And then the next day, the man again, a few days after that, again the man is driving around with penguins in the back seat. But today they are wearing all those sunglasses, including the man. But truth. And lo and behold, they were stopped again by the same policeman. And then the policeman said, "See, I can see right through you through your sunglasses. You are the same person that I stopped you to bring those penguins to the zoo. Didn't I told you that to bring those penguins to the zoo?" And then the man said, "Yes, I did bring them to the zoo. Today, we are going to the beach." Is it funny? Forget about it. Forget about it. Okay, that's funny. Okay, it's fine. We waste some time already. So, okay. So now let's talk about control action. So, see, for a control engineer, his or her ultimate objective is to design a controller which is able to fulfill some design specification. So the specification can be in the form of steady state error, overshoot, rise time, and settling time. So these are the specifications that we want to be met. It can be specified in terms of steady state error. Let's say you want zero steady state error. Sometimes you cannot tolerate overshoot. Sometimes you want a very fast settling time. So these are the objective of control engineer. So the controller input is normally the error between the input and output. So imagine now this is a controller. Imagine now this is us, and the error signal is coming to us. So what are you going to do to make the correction? Say the error is coming. Imagine this is us. So this is information that is coming to us. So what can we do to make a correction with this error signal? So some people say that, okay, we take some action based on the error. For example, we take the action proportional to the error. If the error is large, we make a large correction. If the error is small, then we make a small correction. Those type of action is known as the proportional controller. Proportional meaning that the action of the controller is proportional to the magnitude of the error. So if the error is large, make a large correction. If the error is small, make a small correction. But that is not the only information that we have. We have time in our hand as well. So we can now see how the error signal behave. See, I have my notes here. Okay. So this is, if we plot the error versus time, so some would say, okay, we are going to take action based on the magnitude of the error. If the error is large, make a large correction. If the error is small, then make a small correction. But we also have time in our hand. See, we can also look at the rate of change of the error, which is the derivative of error with respect to time. See, we can predict how the error is going to behave with the change of error with respect to time. We can also make a correction based on the derivative of the error. And then sometimes when the error is small, it is not enough to make a correction. But if you take the integral of the error, finally the integral is going to be large enough to make a correction. So this is called the integral. If we take an action based on the integral of the error, so that is called the integral controller. So in this case, we can have three types of controller: proportional, which is proportional to the magnitude of the error; derivative, which is proportional to the rate of change of the error; and then the integral. This is where the term PID comes from. PID controller: proportional, integral, and derivative controller. So we can use all that. We can use one of them, or we can combine them all together. So mathematically, we can express, see, the proportional controller. See, M is the action signal. If you see here, this is M. M is the signal, the correction signal after the controller. Okay, so now for proportional controller, we say that take action based on the magnitude of the error. And you take the Laplace of that, and then you just get Kp. The integral controller, so the control action is based on the integral of the error. Even though the error is small, if you integrate long enough, then the strength of the signal is going to be strong enough to make correction. So you take the Laplace transform of integral, so you get 1 over s. So Kp is the proportional constant of is the proportional constant. Ki, Kp, and Kd is the proportionality constant. So Ki is the integral constant. So this is now the integral controller, Ki divided by s. And then for the derivative error, so the action is proportional to the derivative of the error. Take the Laplace transform of that, so you have the controller transfer function is KdS. So you can use any combination of this controller. For example, PI controller. So PI controller, you just add proportional controller with integral controller. So Kp plus Ki over S. Some people prefer just, you can simplify that to any of these two forms, depending on your preference. Normally, people would prefer in terms of numerator and denominator, like this, just like the normal transfer function. This is PI controller. This is PD controller. Just add proportional and derivative controller. The idea of integral controller is that even though the error is small, but when you integrate, and then you're going to have enough strong enough signal. The idea of using the derivative controller is that you can predict that using the rate of change of the error, we can know ahead of time where the error is going to be by looking at the rate of change. We can predict that. So there's the motivation of using the proportional control, the derivative controller. And then this is the most popular controller that you're going to hear a lot of: PID controller, PID controller, PID. P stands for proportional, integral, and derivative. You use all three of them together: proportional, integral, and derivative. See, when you use the integral controller, this is 1 over s in the numerator. So an integral controller can increase the type of the system from type 0 if you have an integral, and then you're going to have you're going to increase the type from 0 to 1. So we have seen in the steady state error analysis, see, it is a good idea when you increase the type of the system, then from exist steady state error, you can reduce the steady state error to 0. Okay. If you want to increase to type 2, then you can put double integral. So there's the idea of integral controller. The tuning, the job of control engineer is to choose appropriate value for Kp, Ki, and Kd. So Kp, Ki, and Kd are the design parameter. We can choose the value, the numerical values for Kp, Ki, and Kd. The selection of value of Kp, Ki, and Kd is known as the tuning. You can tune your controller. You can select Ki, Kp, and Kd. There are some tuning method that you can use, which is beyond our scope of discussion in this course. You can always look for how to tune all these parameters. But today we are just, I'm just going to show you an example of different types of controller and how the controller is going to affect our feedback control system. So then there's the idea of basic PID controller. Okay, proportional, integral, derivative, and so on. All right. See here, it is mentioned here. You can use Ziegler-Nichols method or whatever method. And most of the time, people just use trial and error. You can also use trial and error and get the whatever response necessary for your system. Okay. Having said that, let's take a look at this example. Here we have the first order system. The simplest form of system, the simplest form of system to be controlled is a first order, 1 divided by 1 plus ts. And then this is the controller. We can choose proportional controller, derivative controller, proportional, integral, and so on. So this is a first order control system with a unity feedback. Unity feedback meaning that the feedback path is just a unit. There is no h, there's no feedback transfer function. So sketch the time response of this system for a unit step input. So here we have a unit step input for the following control action. So part A, we have this proportional controller Kp is equal to 2. It is selected for us. So this is the analysis type of question. So the controller is selected for us, assuming that somebody select proportional controller equal to 2, and now it's our job now to analyze how the system is going to behave. We want to see how the output is going to behave with respect to time. And then some smart Alex also come in and say, okay, instead of 2, why not we use proportional controller equal 9 and see what happened. And another smart Alex came in, no, that's not good enough. Let's maintain that the proportional controller equal to 2, and then we add some integral with Ki is equal to 2. The integral constant is equal to 2. So we are given this controller, proportional controller equal to 2, proportional controller equal to 9, and then here is proportional controller plus integral. So we want to compare the behavior of our closed loop control system for these 3 types of controller. Okay, so what you have to do is obtain the overall transfer function with appropriate controller, and then for a unit step input, and then you can now solve for the output. And then we can plot that and see how the system is going to behave. Okay, so for simplicity, we just choose the time constant t is equal to 1. Okay, that's just for simplicity. I always like to make my life easier, so we just choose t is equal to 1. Let's take a look at my notes here. All right, so for part A, the controller is proportional controller, Kp is equal to 2. Now we need to obtain the overall transfer function. Okay. So when it is G divided by 1 plus GH. So this is the overall transfer function. The proportionality control is 2, so 2 divided by S plus 1, 1 plus GH, and then you can simplify your overall transfer function, 2 divided by S plus 3. And then for unit step input, U of S is equal to 1 over S, and then you do your partial fraction and take the inverse Laplace, then you get your response. So this is your response, Y of t, Y with respect to time for a unit step input. And then you can evaluate Y of t. Here I evaluate for 4 values of t, 0.3, 0.5, 1.5, and infinity. So this is the value of our response for proportional controller is equal to 2. You can sketch that, you can plot that. Okay, I'm not going to plot that yet. So this is for proportional controller Kp is equal to 2. Then for part B, okay, somebody said, okay, why not just increase the proportionality controller from 2 to 9? Again, you have to go through the process again, obtain the overall transfer function, and then solve for your output and perform the partial fraction, and then take the inverse Laplace of that, so you get your Y of t. So and then you can evaluate your output again at the same time as part A. So I choose the same time, 0.3, 0.5, 1.5, and infinity. So this is the value of your response. And at the moment, this value, we still cannot visualize what's going on here. It is just some numerical value. Until we plot this, we cannot visualize what's going on. But be patient, be patient. And part C, see here we use the proportional plus derivative controller. Proportional plus derivative controller. And again, we still need to get the overall transfer function. See, when you add this integral, you're going to increase from type 0 to type 1. The system is going to increase from type 0 to type 1. But again, we can go through the process. So this is proportional integral. So I always like to put in this fraction format, numerator and denominator, and then we obtain the overall transfer function, which is G divided by 1 plus GH, and then simplify that to this overall transfer function 2S plus 2 divided by S squared plus something's not right here. Yes, yes. Is it right? Is it something's not right? Wait a minute. Oh, okay, that's correct. That's correct. So it's second order system now. It becomes second order system. Second order system type 1. Type 1 type of the system just depend on it's not depend on the overall transfer function, but on the open loop transfer function. If you get the open loop transfer function, see you have the S in the numerator here, that is going to give you type 1. But beside the point, we can now perform the partial fraction, and then this is third order now. You have 3 terms, but one of them turn out to be 0. And now you take the inverse Laplace of that, and then you can now have your output based on this proportional and integral controller. Now you can evaluate that at any particular time. At the same time, so this is the value that you get. Again, you can visualize this until you plot all those 3 responses together. So now let's do that. Now when you plot that, look how nice my plot is. So this is Y as a function of t. This is part A. So this is part A, is the response for the red line here is when we use a proportional controller, Kp is equal to 2. So it is quite slow, and you have some steady state error. So since our input is a unit step 1, the final value is 0.67, I guess. Let's take a look. Here, the final value is 0.667. So you have a steady state error of 0.33. I'm not sure whether this is fast enough or not, but you're going to have this steady state error. But when you increase the controller from the proportionality controller from 2 to 9, here you increase to 9, and then you get the response. And if you plot that, see, the blue line here represent the blue line represent part B, which is we use the proportionality controller equal 9. You can see when you increase the proportionality controller, see, the system is going to become faster. It's going to respond faster, and the steady state error is going to get smaller. In this case, the steady state error is just 0.1. See, by increasing the value of the proportionality controller from 2 to 9, we have made the response faster and then reduce the steady state error. So in that case, you might have an idea that, okay, in that case, why not we just keep increasing the proportionality controller, increase to 20, increase to 100, increase to 1,000. But regardless, you're going to still have the steady state error. The system is going to respond faster, but it's going to be more expensive to construct bigger and bigger amplifier. So you cannot just keep increasing your controller indefinitely just because of the trend here. See, the higher the proportionality controller, the faster the system response, and the smaller the steady state error. That is almost impossible to do, to increase the Kp indefinitely. But see, the last idea here, see, we maintain the proportionality controller to 2. We don't do anything to the proportionality controller. We don't increase to 9. We just maintain at 2. But we add a integral controller, and the value of Ki is selected for us. It is not easy to select this value if given a specification, but thank God somebody has selected the value for us. So now you have the proportional plus integral, and then without even increasing the Kp, you can see in the response here, see, the green line here represent proportional and integral. You can see finally the steady state error is gone, is 0. There's no steady state error. By adding an integral, you now increase the type from type 0 to type 1. The steady state error is gone. It is a little bit faster compared to A, but of course it's slower than B. Slower meaning that it takes longer time to reach the final value. So when design a controller, it is always a compromise. Where do you want to be? If you want a system to respond faster, then of course you need to construct a bigger amplifier. So the whole idea here is explaining the different types of controller. The system is going to behave differently depending on the specification that is going to be given to you. So this example is a very good example at explaining a different type of controller. Of course, the tuning of this PID controller is beyond the discussion of our course. If you are interested, then you can always refer to the topic of tuning of a controller. Okay, so but at least this example illustrate the effect of different type of controller. I can almost guarantee you that this PI controller here is going to be asked in your final exam. See, the effect of integral controller here is to eliminate steady state error. Okay, you can go back to, you can prove that here this is by observation. This is by observation that we show that the steady state error is 0 by observation. You can also derive, you can also prove that the steady state error is 0 using our discussion previously. I can almost taste this. I can almost taste this, that this PI controller here is going to come up in your final exam. Probably is going to ask something like, make a suggestion, how can you reduce the steady state error? Something like that. Maybe the second part of the of question 2, something like that. And then you say, okay, the steady state error can be reduced by adding an integral controller, and probably the question is going to ask you prove that how the steady state error is going to be reduced to 0, and of course you go back and how we evaluate the steady state error. That's beside the point. All right, so do you have any question? Yeah, okay, so that's the end of our chapter 2, right? That's the last example of chapter 2. Tomorrow, my plan for tomorrow, I am lost at y over u step. All right, where is that? Where do you lose? Here. Every condition, the initial one. From where? From where you lost? I am lost. How to get y over s? How to get y over s? How to get y of s? Y of s or y over s? Above it. Y over u. You need to say, please okay. In that case, you need to say, please explain from the beginning. Can you say that? In the beginning, there was dinosaurs roaming the earth. All right, so y over s is the overall transfer function. Y over s is the overall transfer function. All right, so here, this is how you get y over s. If you have a feedback system here, so this is A C, so A over C, so C over A is G divided by 1 plus GH. So this is how you get the overall transfer function. So this is a feedback loop, G and H. So you need to go back to the beginning, where when the dinosaur roamed the earth. G divided by 1 plus GH. Okay. So this is the forward path transfer function is G is now 2, is 2 divided by 1 plus 2 divided by 1 plus S. So there's your G, there's your forward path. Two divided by 1 plus S divided by 1 plus GH. But our H is just 1. So this is just G multiplied by 1. G divided by 1 plus GH. All right. So am I answering your question, or you're getting more confused? Okay, all right, okay. So this is G divided by 1 plus GH. So H is equal to 1. Okay. So G is 2 divided by 1 plus S, because the controller is equal to 2. And the next one, similarly, okay, I got it. Of course, yeah, I skip a few steps already, because assume that we're going to go through the same process with just 9 here. So I don't write it down. So I skip this part for question B, assuming that, okay, my mistake. I know I shouldn't have assumed that. Okay, so this is already skipping a few steps here. So G divided by 1 plus GH, and then simplify that, you get 9S plus 10. Similar here. So this is your G divided by 1 plus GH. H is equal to 1, and then you can simplify that. Okay, do you have any other question? Okay, so that's the end of today. So tomorrow I'll be showing you how to use MATLAB Simulink. Okay, so when we have this block diagram, we can just draw this block diagram in MATLAB Simulink, and then solve that for us. So tomorrow is, I guess, is an optional class. If you want to join, you can join. What do we need to prepare our? No. You don't need MATLAB. No, you don't need. This will not be asked in your test or final exam or whatever. This is just to show you. This is just to show you how to use MATLAB to simulate this feedback control system. All right, so that's the end of today. So tomorrow I will show you how to use MATLAB Simulink to simulate a block diagram. Okay, so I'm going to stop here today. And be on the alert. I will make an announcement when your first test is going to be. Most likely that is going to be postponed, but I cannot promise anything. All right, so I'll see you tomorrow.
Thank you, sir.
Can you repeat the topic? What topic? Topic for the test. Okay. So the topic for the test is up to time response of first order system. You need to complete the first question of the second assignment at least. Okay, you are done with your first assignment. Go to your second assignment and do the first question of the second assignment. That will be on the test. All right, I'll see you tomorrow.